All right, let's start. Okay, so I think it's recording. So hopefully that works. And all right, let's get the show on the road. So first thing is we need. Okay, so here's one of the questions that I just kind of pulled up. So let's see here. And as I read this, I'm just going to copy some stuff down onto my screen that you can't see right now. But so we're looking at this, it says, okay, the mean stat score in mathematics. So they have that the average is 574 normally, with a standard deviation of 31. And then it says a special preparation course claims that its graduates will score higher on average than this mean score. And so the important thing here is this claim, right? The claim is that they can score higher. Do you all know what they're getting at here? Like, what piece of information is that telling us?
It's going to be greater than that mean.
Yeah, which thing?
The 574.
Yes. So which hypothesis, the null or the alternative?
Oh, I'm sorry, the alternative hypothesis.
Yes. 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 Okay. And so that's kind of the key. That's kind of the key. Like, you want to look at and see if I can move this over here. You want to look at and see what are the researchers claiming, and whatever the claim is, that's going to be your alternative hypothesis. So so you've got the H naught, which is the null, and the H1, which is the alternative hypothesis. So what I want to put for the alternative is I'm going to say that, okay, we're claiming that the mean is greater than 574. Okay, and so when you're writing the alternative in the null hypothesis, the null is always going to be like an opposition to the alternative. Okay, so for us, the null is going to say that the mean is going to be less than or equal to 574 is what the null is. Okay, so that's how you build these two things. So you look at like the language of the problem, and one of the first things that I look for is like, what are the researchers, what is the claim? And whatever that claim is, that goes in as the alternative hypothesis. And it'll either be like a claim of greater than, or a claim of less than, or a claim of not equal. So those are like our three options in that space. So coming back to the problem, so they say, okay, so they claim that their graduates score higher on average, so that they think that they can give you a better mean. So then they take a random sample of 11 students. Now, what's the issue? That should kind of immediately throw up a red flag. What's the worry with that?
Isn't the minimum like 30 that you need for a sample?
That's right. That's exactly right. So if they're saying that their sample only has 11, then technically we're not even allowed to use these tricks because we can't have any confidence that the sampling distribution will be normal. But then they do tell us right down here, they say assume that the population is normally distributed. Okay, so with that assumption in place, we can go ahead and like accept the sample of 11, but normally that sample would have to be greater than 30. And if it wasn't, and they didn't tell us we could assume normality, then we would just reject this and say you can't even do this study because the numbers won't work. So okay, so we're going to say fine, sample of 11. And let's see, sample of 11 students. And so for them, when they took a sample, they got their sample average to be 583. Okay, so assume that the population is normally distributed, and we're testing at a significance level of 0.05. And that's kind of industry standard. This 0.05 means that they're taking a 5% risk that they're going to be wrong. Or if you're thinking about this in terms of like type 1 errors, you have a 5% chance of committing a type 1 error. Okay. So then, can we conclude that the preparation course does what it claims? Assume that the standard deviation is also 31. Okay. So now let's dig into this and see kind of what's going on. I've tried to copy down all the important information. So at first you may say, hey, look, that's 583. The original average was 574. So can't we just say that it's greater and move on? Well, the problem with that is, I mean, we're just taking samples. And so we have this thing called the sampling distribution of means. Oh, is there someone trying to get in? This thing like beeped at me.
Sorry, that was my phone.
Oh, I heard a beep. Where's my, I got the toolbar to appear once. Where's the toolbar? Oh, there it is. I don't see anyone. Okay. Okay, so the sampling distribution of means is always normal. And what we're going to kind of make this, we're making the assumption that the middle of this thing is this value 574, okay, which puts this thing over here at 583. But these are just samples. Really, we don't know what the actual sampling distribution looks like. We're just testing this against kind of like this theoretical one that we've built here. And we're doing, can you tell if we're doing a 1 or a 2-tailed test at this point?
Yeah, isn't it a one-tailed test because you've got just the greater than?
Yeah, absolutely. Yeah, so we look right here, and it's just a one-tailed test. And we would know, well, we would know a little bit more about this if, so for example, if this was like not equals 2, then that's a 2-tailed test.
Yeah.
Or if it was less than, that's also a 1-tailed test, but it's testing the other side of the distribution. So right now, since we're doing the greater than, we're testing this side of the distribution. And we're trying to see our value, this 583, we want to know, where does it fall? Does it fall over here, or does it fall down in here, right? Where is that value going to appear in the distribution? If it comes down in here, that's the region of rejection, and then we can reject the null, and we're good. But we don't know that just yet, okay? Now, some of the other things that we've been told, we have this alpha level, okay? And what this is saying is, number one, we're taking like a 5% chance of being wrong. So this is the same as 5%. What this means is that this area right here is 5% of the distribution, which means that all of this area is 95% of the distribution, okay? And in order for us to reject the null, we need the proportion. So this is what we're trying to test. We need the proportion of this thing to be within this area here. Does anybody have any questions about that before I move on? I know that this stuff can get kind of sticky.
I'm just wondering, so what are the signs that tell the difference between a 1-tailed or a 2-tailed? I think in the examples, like for the homework, it just told us like one side or two side.
Okay, so when you're setting up your alternative hypothesis, you want to look here. If it's a greater than or a less than sign, these are one-tailed tests.
Okay.
And if it's not equals, that's your two-tailed test.
Okay.
Okay.
And then equal to, would that also be two-tailed, or
Well,
those are the only signs?
so you'll never see an equal to in the alternative hypothesis. You should
Okay.
only ever see one of these three. But if it were to, no, I can't up here. So it's
Okay.
it's either going to be greater than, less than, or not equal. And then that tells you what kind of test you're doing. And if it's the greater than sign, excuse me, this is less than. If it's the less than sign, then you'd be testing on this side of the distribution. When it's the greater than sign, like what we have, you're testing on that side of the distribution.
Oh, okay.
Okay. Go ahead. Any other questions about this before we keep going? Okay. So again, kind of the really important thing here is like, I need to use this significance level, and the symbol for that is alpha, to figure out like how much percentage I need to put in this area here, okay? And since this is 0.05, I know that it's going to be 5%. And so now, like if you look at the rest of this problem, we filled out the null hypothesis, we filled out the alternative hypothesis, the type of test statistic, there's a bunch of weird stuff in here. We only do z-tests, so this answer is always going to be z. If we went further in the class, we'd look at some of the other ones, but we only ever do z-tests. So if you see that on the exam, you know what the answer to that one is.
At least you get 1 out of the 6 automatically right.
Exactly. Yeah, we only do z-tests. So that's that one. This one here, the value of the test statistic. Okay, so that's what we need to compute. What is the critical value? Okay, and so computing a critical value, or like the value, excuse me, it's not the critical value. This is the value of the test statistic. Let's see here. It's just like finding a z-score. Okay, so the value of the test statistic, I'm going to take this thing here, x bar. I'm going to subtract it from this number that I'm testing everything against. So I'm just going to call it mu. And then you divide by the standard error, which is the standard deviation divided by the square root of n. Okay, so for us, these numbers are going to be 583 minus 574. Now, well, okay, if you look at this, if you look at the computation on top, 583 is bigger than 574. So we know that that's going to give us a positive number. And that's good, because if you look over here at your distribution, we're on the right side. And so we know that those need to be positive values. If we were testing something over here, then that would come out negative. And that's what we would expect. But so far we're on track, right? We've got a positive value. Go ahead.
Do you mind sharing your
shoot. Sorry, I forgot. You can't see that? Okay. Okay, sorry about that. I forgot that it was covered. So I've got z. Okay, so here's x bar minus mu over the standard deviation divided by the square root of n. And now looking at, okay, any questions of where my numbers have come from so far? Okay, so it told us that the standard deviation is 31, then divided by the square root of our sample size, and that's 11. Now, when you're putting this into a calculator, be very, very careful. I always, like, if I was entering this, I would definitely put all of that in parentheses. I would definitely put all of that into parentheses. Be really careful when you put this into your calculator, or you may make a calculator error. So let's start here. So you can't see my calculator, but, well, I guess I could hold it up. Look, here it is. Minus 574 divided, oops, I want this to be divided by, and we're going to divide this by 31 over the square root of 11. And I am getting this z to be 0.96289. And, oh, I don't know, you might not be able to see that. I've got too many things on my screen here. Okay. Okay, so you look at this, and what this is saying is that this value, this 583, it's not even quite one standard deviation away from the value we're testing it against. One standard error away from it, I guess I should say, because this is technically a standard error, not a standard deviation. And so this is the number that I would put into this. What is the value of the test statistic? And it wants me to round to at least 3 decimal places, so I'd put in 0.963, because that would round up. And then the last thing it asks is, what is the p-value? Okay. And so this is one of the things that somebody emailed me about and asked me to talk about this. So now that I have this z value, hold up, let me go back to my 0.963. 0.963. This is my z value. This is this test statistic. And I need to turn this into a p-value. And then hopefully, I have not clicked on it in a long time. Oh, I'm still here. Okay, good. Can you all see this?
Yes.
Okay. So I just opened up a random thing in Alex just so that I could get a hold of their calculator, because their calculator does some really cool stuff. So we just computed this z value, and I need to turn it into a p-value. And what that is it's a proportion. Okay. I want to know. Let me go back. I want to know. So here's the distribution. Here's the mean. Here's my test statistic. It's right here. What the p-value is that's asking what is this proportion? What is that? Like that's what when it asks for a p-value, that's what it's asking for. Value. It wants to know what proportion is that, okay? And so to do that, I can use this little calculator. If I click on Z, then I can type in 0.963, and that'll give me the proportion for a Z score of 0.963. Wait. Hold up. Let me see what this. No, that's not what it does. I need this button. Oh, I see. These. I normally, if you've watched my videos, I normally use the tables. I never use the calculators. Okay, what this one does is if you put in a proportion, it tells you the Z-score. So for example, if you put in 0.5 as a proportion, it'll give you a z-score of 0 because that's right in the middle. That's right at the mean. But what we want the proportion. Okay, so our z-score is 0.963. And then the other thing to notice is okay, so it gives us a proportion of, so our p-value is 0.832. Okay, now let's see what that means. And notice, do you see how this is showing this less than or equal to sign? That's important. So when I go back to my distribution, it gave me this p-value here. But since that thing calculates the p-value of a z-score that is less than or equal to, it gave me the proportion, it gave me this proportion. So that this number is the 0.832, or it's 83.2%. But I need to see what's on this side. Like, that's what we're really testing. So I need to get my calculator back out, and I'm going to go 1 minus 0.832, or yes, equals 0.168. Okay, so this is this area here, 0.168. And so in my problem, whoops, wherever it went, right here, this p-value that it asks for, what I would type in is the 0.168. Okay,
Wait,
does that make sense? Go ahead.
So I understand with the button, the p-value button, where it's less than or equal to, or greater than or equal to.
Mm-hmm.
And then but to know if it's 1 minus, are you looking at your original claim score, or how do you know?
Oh, okay. So what I'm doing here is, so in this distribution, I know that all of this area adds up to 1. Okay. Mm-hmm. And when I put that thing into my calculator, I know that my test statistic is here. And so I'm either going to get a number, like I'm either going to get a big number or I'm going to get a small number. And what it gave me is it gave me the large one. It gave me the 0.832. So I knew that it gave me this part of the thing. Does that make sense? And I know that 0.832 plus whatever this is has to equal 1.
Oh, okay.
And so I subtracted this value from 1 to figure out what that last little bit is.
So is that because the area is the 0.05 that's on that right side? Or
okay, so this is the interesting thing. Okay, so now when I make my comparison, okay, here's my normal distribution. This is not. I've been trying this for a while. You think I'd be better at it? Okay, I found. Okay, my test says that I have to be over here at 0.05, right?
Yeah.
And when we did this calculation, we found an area of 0.168.
Mm-hmm.
And so you see how I am greater than the allowed region of rejection?
Yeah.
Okay. And so because that's the case, this is a situation where we fail to reject the null hypothesis. I don't, hold up. Here, this is the problem. So I think that there's another, maybe there's not. Normally there's another box under here that asks like, can you accept the claim that they're making or not? And here, I cannot accept the alternative hypothesis, which is that their preparation program works, because I fail, like, based on my graph, like, we're way outside the region of rejection, and so they can't make, it's not a legitimate claim. Like, for that little group of 11 people that they sampled, sure, they did score a little bit higher than the average, but but they didn't score high enough to say that the whole population is doing the same thing. Does that make sense?
I think so.
That's a marvelous answer. Well, that's kind of what this is all about. Is like I wanted this proportion to come in here, to be smaller than the red one. Like, and the thing is, it's like, I mean, look at these numbers. This is 0.05, and I got a proportion of 0.16. This is way bigger than that. Like, we are, like, I mean, if I were to color this green thing, I probably should have colored it way out to here. Like, we are way not even, we're nowhere close being able to reject the null hypothesis and to accept the alternative. You know, because if I go back to my original study, the alternative hypothesis is that, hey, they are scoring more. But it's like, nah, I can't say this because maybe this is still true, that it's actually less than or equal to, right? They may actually be doing worse. And it just happened is that the number of people they sampled showed something that's greater. But I don't know, right? I have to stick here and have to say, you know what? I can't reject the null, and I definitely can't accept the alternative. So their claims are unsubstantiated.
Is that simply because of the sample size is so small? I mean, if you got a larger sample, you could make that claim easier. Is that? Or depending on the data, I guess, obviously.
Yeah. So it depends on the data that comes back. And the small sample size is very worrisome. The larger, and so that's the thing. The larger your sample, it plays it like that plays around with this value here. You know, because if I put in 50 down here, that would totally change the z-score I got. And so larger samples do make it much easier to substantiate your claims. But like that should make sense, because like if I surveyed 50 people compared to 11, and I found that 50 people were getting this score, the 58.3, that's much easier to believe that everybody's doing at least that well compared to just finding 11 random people. Does that make sense?
Yeah.
So yes, you're absolutely right. Larger samples do make it easier to substantiate the claim that you made. But then also by taking a larger sample, you get different data, and that may shift this score because the whole thing, what we're trying to do is we're trying to get closer and closer to the true mean of the population. And so, I mean, so that's what this is all about. Any questions about any of this process?
No, that was really helpful to see how to solve for the p-value, because that was the one that was really tripping me up a lot.
Was it getting this part, the 0.83, or did you not know to like grab the other side of the distribution, like to take the 1 minus it?
I think that was where I was kind of tripping up.
Okay. Yeah. Alex probably isn't like great at at pointing you in the right direction.
Yeah.
With this, but yeah, when you first get that p-value, you want to look at like what the original distribution is and kind of just like think reasonably about, okay, if I know my score is somewhere over here, what side of the proportion did I get? Did I get the left side? Did I get the right side? And which side do I actually want?
Mm-hmm.
And in our case, because we're testing on the right, we need the right side of the proportion to make a comparison.
So if it were the opposite, if we were looking at the left tail, then when we did that calculation in the Alex calculator, that answer that we get would be the p-value.
Exactly.
So if we were looking for the left and we got the 0.832, then we would know that that was our p-value.
Right.
Okay.
That's exactly how it works.
And then likewise, because if it was the right side, it'd be 1 minus p-value.
Yep, always,
Okay.
always 1 minus.
Okay, I think it just clicked.
Nice. Write it down. Hurry and write it down, because sometimes like it clicks and then like 5 minutes later, it unclicks. So whenever you have that like epiphany, like write down whatever it was that clicked so that you can return to it. And so that's the thing, like as you're preparing for the final, really the questions that you'll see in there are exactly like the ones you've been practicing with. So if you've taken some time to like take notes on how to do those, especially the problems in modules 6 and 7, you're gonna do great on the final. So that's my 2 cents on that. Is there anything else that you all want to look at?
Let's see.
So how about the same type of problem, but when the answers, so instead of p-value, you do the critical value? How would you do that?
So, okay.
Yeah.
So, okay, looking at critical values. Do you want to use the same numbers and just have me find a critical value for it? Or
Yeah, that's fine.
A whole different problem?
I think you could just use the same numbers.
Let's see. And do you all know, like that you can click this little arrow and you can see all of the learning objectives, and you can scroll around to see what so I've had some folks not know like how to navigate. And let's see here. I mean, so this is technically what we're doing. And this one, this one wants a p-value. Can I reset it to give me a critical value one? I don't know if it will let me do that. Let's just go back to the example we have, and we'll find the come back here. And okay, so if I was doing this with a critical value approach instead of the p-value approach, actually, let me just clear all of this. And okay. So the one big difference. So here's our distribution. There's the mean, and I know that my alpha level is 0.05. Okay. If you've seen my videos, let me find it. There is a table you can use that makes this super easy. Whoops. So I put this table in my videos, but bring this back. Okay. So check this out. We're at a significance level of 0.05. So I can just come over to this chart and I can say, okay, I'm at a significance level of 0.05. So I know I'm in this space. This would be, you know, this is a 5% risk. This is a 10% risk. This is a 1%, a 2%. But we're here in the 5% risk. And then you can look and see, okay, what kind of test am I doing? Is it a left tail, a right tail, or a two-tailed test? And really, these are the z-scores that match this proportion, okay? So for us, since we're doing a right-tailed test, we want that value. So over here, you know, we are, so pretend this is 1 standard deviation. So this 1 standard deviation pretends that maybe this is 2 standard deviations. So we're right here in the middle somewhere. So our critical value has a z-score of 1.645. And that puts the region of rejection, all of this stuff. And this area would have to be or that proportion, excuse me, 0.05 would be that proportion, which means that all of this is how much? What's that proportion?
So then would I just plug it into the Alex calculator at that point? Or are you done?
Well, okay, so we're not quite, I mean, we're not quite finished yet. So we've just found what the critical value is, and we still need to compare the test statistic to it, okay? But what I'm trying to say here is, if I know that this proportion is the 0.05, right, that comes from my significance level,
Yeah.
what's this green area going to be, just based off of what we know about proportions?
It's 95.95.
Right. Yeah, 0.95, right? Because these two things have to add to 1, always. So it's like I have 95% to the left, I have 5% to the right. Does that make sense?
Yep.
This is just, I mean, we don't need to know that to finish this, but it's just kind of like, just testing, like, what do we know and what can we know? Okay, so here's my critical value at 1.645. Now, I calculated this z-score. This is the test statistic, right, that we calculated before? Because, oh, you can't see that. Do you remember running this calculation and where these values came from?
Mm-hmm.
Yeah, we just
Okay.
plugged it in from the story problem.
Yep. And so this is my test statistic. So now I want to compare my test statistic. So it's 0.96. So that's going to be, let me do it in blue. So if this is 1 standard deviation, 0.96 is right here. And check that out. Am I anywhere near the region of rejection?
No.
No, right? I would need this blue line to appear in here in order to reject the null. And we're way over here, less than 1. And so thinking about this in terms of critical values, I'm comparing 0.9, what was that? 0.96? 0.96 to this 1.645, and it's much less than it, and I need it to be greater. And so that's how the critical value approach works, is you find what that critical value is based on, you can look it up in this table based on your significance level. And then you want to compare the test statistic to it.
Okay, but is it done? Like, would that be the answer, or do you still plug it into P?
Well,
Like
so now, I mean, I know the proportion to the left of the 1.645. That's this. That's my significance level.
Is which number?
So the proportion to the right of 1.645 is this, the 0.05. It's the significance level that we were given.
Okay.
And so the only thing that I would need to find a p-value for would be the 0.96. But that's what we did in the kind of the first part of the problem. And we found that it was a lot bigger than that. So whenever you're doing critical values, you'll just compare the test statistic directly to the critical value. And then remember that you get the critical values by looking at this table.
Okay, so I'm comparing and I see that our critical value is less than the statistic. Oh wait. Or 1.6 is the critical value. Never mind.
That's,
right.
Yeah.
Right. Okay, so our statistic is less than the critical value. But I feel like in the homework, like it made us compute something and it had, like, I just don't know if that would be the final answer, I guess.
So you might have had to compute this, that what the actual critical value was. And for me, like these will never change given like these significance levels. Like, so if they gave you a random significance level, so if they said, hey, the significance level is 0.03, then since that's not on the table, you'd have to compute that. And to do that, we just need our calculator. I would go over here and I would say, okay, so let's say that the critical value, that the significance level was 0.03. So I'd put that in here. And notice it gives me this large number, but I don't want, this is the left side, I need the right side. So I'm going to go 1 minus that. And so this would be the value that I actually would be comparing against.
So are you basically, like with critical value, are you basically just proving whether it's true or false? Like if it's, like if the critical value was more than the statistic, so it would be, I'm trying to think, our original, so it was greater than, so then it would be true because it was greater than?
Well, okay, so to tell whether or not you're true, like you need to look at your thing and we need to say, hey, is my test statistic, is this inside the region of rejection? And since it's not, yeah, so since it's not in the region of rejection, then I cannot reject the null hypothesis. So their alternative hypothesis is not true.
Okay.
And I would be careful with like, so because for example, if we were testing on this other side, so let's say that the critical value was here and my test statistic is here. So that test statistic is in the region of rejection if we were doing a left-tailed test. But then this thing is also less than, does that make sense? So yeah, so be careful with trying to like make a blanket statement of like being less than or greater than. You just look to see, are you in the region of rejection or not? Does that?
Okay.
Yeah, I always draw the distribution because without it, like there's too many places to make a mistake. I just need to see it.
Okay.
Any other questions about this stuff from anybody?
I don't think so. That was really helpful.
Okay. Well, thank you so much for attending. This has been great. I will figure out how to post this video that we recorded, and then I'll blast it out in a mass email to everybody, so that they have this if they want to look at it for the final. And then good luck with the final exam. And like I said, the questions in the exam are exactly like the ones you've been practicing with in learning objectives. So if you feel comfortable with those problems, you're going to do very well.
Thank you.
Yeah, no problem. Let me know. You can send me an email if you all need anything. And good luck. And I'll see you around maybe.
Great. Thanks, Adam.
Yeah,
Thank
no
you.
problem.
Thank
Bye.
you.